Good evening, everyone. We are the team Vatos Locos. The members include Alexander Pustinger, Ayushma Timnisiana, Corey Marquez, Jesus Moore, and Lynn Acosta. We are current undergrad students in the mechanical engineering department taking mechanics statics at the University of Texas at El Paso. So the project we are doing is called the Extronaut Challenge, and the objective of this project is to design and construct a lander utilizing structural analysis. The design and construction of the Mars lander must contain an extronaut that is secured within the frame. The mission is to safely land Eggstein and his Mars lander from a drop of 1 meter off the ground.
Good evening, guys. This is Lynn Acosta. So here I'm going to go over the design requirements. As stated before, the minimum drop height is 1 meter up from the ground, as well as the maximum weight that your lander cannot exceed is 450 grams, and the maximum landing pad it has to land on is 300 millimeters by 300 millimeters, and the cross section must not exceed the surface. Another requirement we were able to use was 8 grams of CO2 canisters. We did not apply these canisters to our structure because it was first of all, it was very difficult to really implement these canisters onto our structure. And another requirement was that we can only have hot glue at the joints and not along members. We also were not allowed to paint the lander, but we were encouraged to paint the extronaut as we desired.
Good evening, everyone. My name is Jesus Moore, and so right now I'm going to be talking about the brainstorming ideas that our entire group had as a whole. And so the different brainstorming ideas that we had. So all of us, we were going to build at least one prototype from each group member, and we were going to present each prototype to our group members. Our group conversed about the advantages and disadvantages of each of the prototypes presented. The design requirements were considered for each of the prototypes to evaluate which one would be the ideal prototype. And while deciding the prototype we would choose, the deciding factor was weight. Weight was heavily discussed because we wanted it to be light enough to have flexibility, but also strong enough to be a very sturdy and stable structure.
So for each team member, they all submitted a prototype. And so here for the first prototype, as you can see, it has a better secure design, but we decided that it would be more better to use this as a basket for our egg. We decided we needed to have an outer frame for the egg to not be at the base. So the only cost was it was less work and less pasta. For the second prototype, as you can see, it would be a perfect frame for the egg. We could incorporate the first prototype here as a way to hold the egg into the place of the center of this frame. The second prototype had a good base area and the egg was not directly at the base, so less impact would go on the force of the egg. The cost was more work and more pasta, but it was worth it.
So for prototype 3, we decided there was an idea of having an angled force member. And so we really tried to really work with this and try to implement it. But we couldn't really figure out exactly how this would work. So we actually just picked up this idea and we applied it to our final design. The good thing about prototype 3 is that it really indicated to us that we would need a parachute. And the cost with this is that just as the first prototype, it would be less work and less pasta as well. And then for our fourth and final prototype, it we the group introduced a triangular cage idea for the egg. And we at first considered the triangular cage But then we began to think about, should it be triangle, square, and this is an idea that we were revolving in our heads. But this prototype 4 did make the base constraint with each other to maintain the center of gravity, which was good in the overall design. And the cost with this was that it was less work and less pasta as well.
All right. So now we're actually going to go into our first ever design in our design draft that we incorporated all the different prototypes. The chosen design draft was an incorporation of all 4 prototypes. The design was just the way we had envisioned it. The first design draft weighed 58 grams without the egg, but including an egg, the total weight was 120 grams. When the first design draft was completed, it was time to put it to the test. We tested the design at a drop of 1 meter, and did it survive? And it did survive, but received substantial damage. We glued the pieces of failure and decided to test the yield point of the structure by dropping it from the bridge. The bridge drop provided us with ideas for vital design modifications to the structure, such as the use of a parachute, stronger and additional members to the final design. So, kind of to go on this same point, we realized that whenever we actually dropped it from the bridge, our Mars lander was successful in the sense of it landing still on its base, which was something that we wanted to achieve, and that allowed us to stick with our design and just add a little bit more so that our egg would survive the next time that we actually test it.
So a couple of things we had to consider when designing the prototype here was we had to consider potential energy, which is the mechanical energy that a body has by virtue of its position. As for the formula of potential energy, it equals mass times gravitational acceleration, which is 9.8 meters per second squared, times the height. The next thing we had to consider was the kinetic energy, which is the mechanical energy that a body has by virtue of its motion. And the formula for kinetic energy is 1/2 times meters time, it's 1/2 times mass times velocity squared. And the final thing we had to consider was the impact force, which is the force generated at the start of contact collision. So we needed to account for all of this so we could figure out a way to both help slow down the acceleration as the lander was coming down from the 1 meter drop, as well as seeing how much of the impact was going to hit the frames so we can actually build a strong base.
So here's our final design. So the final design, as you can see, we did add plenty of additional members, and as well as we decided to go with the basket and then encage it around it with the egg inside. So the dimensions for the final design is that it weighed 191 grams total, including the egg. And the cross-sectional length actually was maintained at 300 millimeters. And the total height was 160 millimeters. And while we were constructing it, we figured that one of the key features was the idea of constructing the basket in the center of the structure, which would actually, when it would hit, it would actually maintain the mass right in the center, and we wanted to the impact force to go to the outside and create the most maximum surface area. And the second key feature was the addition of the parachute. In the first drop, we did not incorporate a parachute, which really caused it to really maximize the impact force, and the addition of this parachute created a drag to slow the descent. So slower the fall, the less the damage.
So now we're going to show you a video of us testing out our final design of 1 meter, and it's successfully landing exactly the way we want it, and also keeping the egg safe. Go ahead.
1, 2, 3.
Go ahead.
All right. So to kind of go on with our project, um, we did a lot of analytical calculations to make sure that the forces, the force of impact that would occur upon our structure would not affect the cage of the egg at all. And so our friend Alex Putzinger did all our math for us to ensure that the joints were either at tension or compression, and to ensure that our egg had a successful landing. And so as you can see here with the analytical calculations, the impact velocity was going to be 4.27 meters per second. He more than likely used a kinetic energy equation along with the potential energy equation. He found the work, and then he found each individual joint, which you could see in the math on the other slide, and he stated whether those joints were going to be in tension or in compression. All right. So, part of our project was to create a simulation of our truss system using one of the different modules that actually allows us to test it using trusses. For this one, we used Fusion 360. This was a design program to build our truss system and to determine the static forces that would act upon this system. We used Fusion 360. I personally had learned about it from my first engineering intro to engineering. And as you can see in these pictures here, I labeled out the different dimensions to ensure that our design was as accurate as we possibly can get. I just also created it into a 3D program. Fusion has a certain program that allows individuals to check the loads that act upon the truss system. I use a mass of our truss system, which was 191 grams, and multiplied it by gravity to find the force. I assume that since it's going to be at the center of gravity, I put that force upon the center, which was 1.87 newtons. Fusion automatically showed me how that force would act upon the base of our truss system, and from there we had an idea of what joints would break upon impact. We also discovered that the force of impact will distribute away from our cage. Moreover, within the requirements that you had given us, you wanted us to assume that spaghetti was 10 to the 5th pascals. Unfortunately, I wasn't able to find a particular material that was at that grade, so all I used was ABS plastic, which was the closest in pascals to what you wanted us to do.
So here for the final test of the Mission Extra Local. For the 1 meter test, as we can see, we successfully completed our objective of dropping our egg as well as a Mars lander 1 meter above the ground, with it successfully surviving while even though one string of Paso broke from the side, which didn't damage the Mars landers much. So for the 1 meter test, it was successful. For the 2 meter test, our egg survived with no cracks on it. However, our Mars lander broke at one side of the base, but the little basket that was holding the egg remained intact. So we had completed the 2 meter test as the egg had survived.
So this brings us to our 6 meter test, the bridge test. So we went up to the bridge and we dropped it. When we found out, it actually, from the 2 meter test, it did have some damage, but we decided to go with it. And with the understanding of the impact force, the egg basket in our design stayed intact actually from the bridge. It actually separated from the actual structure, but the basket did land at an angle, causing the egg to break in the basket. But the basket did stay intact. The egg just couldn't survive the impact. Thus, the bridge test was unsuccessful. But it did measure exactly. It actually met our expectations of what would happen.
Alright, so in conclusion, with all the design requirements, we were able to construct a fortified frame around the egg to withstand the impact of the ground from 1 meter off the ground. With the proper members and supports, we were able to create a proper equilibrium structure around the egg, which was absorbed the majority of the impact, leaving minimal forces to go to the egg's basket and damaging it. So with this, I would say that our Egglander was successful. Of course, I think there could have been things that we could have improved with our structure, but all in all, I am very happy with what our group had to bring, and I hope to do projects like these in the near future. Thank you.